So let's talk about differentials, and it's going to involve this expression here, and then we're going to have this expression right here. So what I want to do is I want to go back to this one first and go just a little bit back to Cal 1. So in Cal 1 you had some function here, f of x, and the idea was to approximate the function using the derivative. So if f of x may have some nasty looking expression, who knows? I don't know, f of x sine x plus ln x minus 1 over x or something crazy. What the derivative allowed us to do is to approximate this gross expression with a nice linear approximation to it. And so the other videos talking about this, there's another video that talks about the linear approximation to it, which is basically just your derivative times x minus your point plus y plus your b. Okay. All right. Now that's for another day, but let's go back to this. So what the derivative did was it allowed me to approximate the curve in a really small little area here. Okay. Yeah, it's a little small area right there. It approximates the curve. Now, if I were to take this idea and extend it a little bit, like let me redraw it over here so it's a little better. If I were to do it like right here instead. All right, so there's my tangent line right there. And now if I went up, if I go over a small amount dx from that, all right, so let's suppose this is a, and let's go over another amount, and we're going to call this delta x, that's that h. So we go up to the curve, up to the curve. We're going to call this point P. We'll call this point Q. So the derivative is will the tangent line, okay, will give you an approximation to the slope from one point to another. Okay, so if you look at this, the slope from P to Q, if you go further down the graph, the slope from P to Q is going to be just the slope of the secant line there, which we found to be in college algebra. Let's draw it down here. We call that delta y over delta x. It's that y2 minus y1 or x2 minus x1. That's what that is. What the derivative can do for us, though, is find that same slope as an approximation. So approximate that same slope. So the derivative, recall, was the slope of this line instead. So this right here, this delta y over delta x. Let me draw that in purple. Delta y over delta x. That is the slope from one point to another. That is the slope of PQ. What I can do, though, is I can approximate that slope using the derivative of the function instead. And so I will do that in blue. So now this slope here, that is dy over dx. And that is dx is here, and dy is there. So if you look, I'm going to compare these two triangles. Let's draw the other one here. So this is dy, and this is dx. And so dy over dx is an approximation of delta y over delta x. So if we are looking at a little change from one point from my function to another, then I can calculate the actual change in the function itself. All right. So this is how we're going to do it. In Cal 1, what you did was you said, okay, dy over dx was, well, let me draw that in blue because I've drawn those in blue. That was dy over dx was your derivative, f prime of x. It's equivalent, it's an equivalent statement to say that dy is f prime of x dx. So these, we're not multiplying both sides by dx, it's just an equivalent statement. So how this helps us is if the derivative is a simpler function, then calculating this change in the function itself from one point to another, the change in the function itself from one point to another is probably going to be easier using the derivative instead. All right. So the idea here is given in this graph from, I just took this from the book, and it's the same thing I just wrote. So the counterpart in Cal 3 is surfaces, of course. So you have this nice surface here, and what I want to do is I want to take that surface and I want to approximate it using a tangent line. I mean, tangent plane this time, a tangent plane. And so if I am going from one point P to another point Q, so I'm going along, it looks like, no, I'm sorry. No, that's right. So if I'm finding the slope here, right, I can approximate that slope. Okay, so how did I draw it? I think I drew it in the other one in purple, right? It doesn't matter. I can approximate that slope using the tangent line instead. I mean the tangent plane instead. So that slope there. All right. So the idea here is probably better explained using an actual example. All right. So let's see here. Which one of these would be good? Let me do 33. Okay, it says the length and width of a rectangle are measured in 30 and 24 centimeters respectively, with an area measurement of most 0.1 centimeters in each. Use differentials to estimate the maximum area and calculate the area of the rectangle. So the area of a rectangle, let me choose a different color here. The area of a rectangle is the length times the width. So I'm going to call that x times y. So length is x, width is y. All right, length times width. So what I want to do is I want to find, okay, so the area is 30 times 24, which is 720. All right, it says here there's an error in measurement of at most 0.1 centimeters in each. So the change in x can be 0.1 plus or minus, or and the change in y can be at most 1 centimeter, 0.1 centimeters. All right. So the question is, how does the area change? How does the area change if, no, according to these differences? All right. Well, you can calculate this, right? This is pretty simple. I'm doing a simple problem because I just for illustration purposes. So I'm going to take my A. Let's change it. I'll take my A, and now I'm going to say so A. So the change in A. So the new A. We'll call this A sub n, new A, capital N. That's going to be 30.1 times 24.1, or I can do a subtraction of 1, or I can do negative in these. Okay, so I multiply these two together on my calculator, and I get 725.41. Now, if you compare that to the original, if you compare these, the difference or the change in the area is 5.41 square centimeters. All right. Now, what we could have done instead also was we could have done -1. So area new could have been 29.9. times 24.1, in which case we would have gotten, let me do this on my calculator right quick, 720.59. But you notice that that's not much different than the other. I'm just changing x and y in 0.1 distance either way, plus or minus for either one. But the most they can change is 725.41. And you'd get the same answer if you went the other way. If you did 729 times 23.9, you'd get 714.61, which is a difference from 720 of 5.39. All right, so very similar. All right, so there's a better way to do this. So what we did was we calculated the area using the original terms here. We got 720, and then we calculated the area using new ones here. We got a new area there. So there's another way to do this, and it involves differentials in Cal 3. So what we can do, if you remember, so we have this dy over dx was f prime of x, and so this led to dy equals f prime of x dx. Okay, so now in 3D you have f z equals f of xy, so it's a surface now instead of just a curve. So I'm going to rewrite, I'm going to write the same thing I wrote up there, but in terms of z. So dz dx is, now I'm going to suppose that y is a constant. Y is a constant. All right. So just for a second, since y is a constant, and I'm going to suppose that x and y aren't attached, like it's not x times y squared or anything like that. So if I write just what I wrote up at the top, it would be z prime of x, which we write as the partial of z with respect to x. All right, now I'm going to do the same thing for y. So partial of z with respect to y is, or derivative of z with respect to y. Derivative of z with respect to y is z prime of y. And that can be written as partial of z with respect to x. All right, now, if I put all this together, so if I take this dx and I uncouple it from the dy over here, I get dz equals partial z with respect to x times dx. And if I do that on the right here, I get dz is equal to partial z with respect to, I'm sorry, this should have been y. With respect to y times dy. Now, using a little bit of advanced calculus, we get the total differential. It's called a total differential. All right, total differential is partial z with respect to x times the change in x plus the partial z with respect to y times the change in y. Okay, and so what this is going to do for us is it's going to show us the change in my surface from one point to another, the change in my surface from one point to another using the differential instead. So instead of calculating this red line here, I'm going to calculate using this green line here. And this right here, this change here, is going to be the difference between delta z and dz, okay? Change in that. So this is the actual, that's the actual, and this is the approximate. So what we're doing is the approximation of this. So let's go back to the other one that we had, this area formula here. All right. Okay, so I'm going to write the area. So now that's going to be our z. So I'm going to write it. So let's do it using differentials. I'll use purple again. So a is x, y. So remember our formula is dz equals the partial of x with respect to x times dx plus the partial of z with respect to y times dy. All right, so in this case it's a. So it's dA is z a sub x dx plus a sub y dy. Now, a sub x in this case would be just y, just the derivative with respect to x, times dx plus, and then x times dy. So in our model up here, it was 30 and 24 and 0.01. I mean 0.1. So it's 24 times 0.1 plus 30 times 0.1, which would give us 2.4 plus 3.0, which is 5.4. All right, so the change in the area would be 5.4 if my x value changed to from 24 to a change of 0.1, either way, and then my y value from 30, or the other way around, 30 and 24, doesn't matter, it's the same work, y equals 0.1. So we got 5.4. Now, when we did that before with the actual, we got 5.39. So, and 5.41, right? So it just depended on which way we went, minus 0.1 or plus 0.1. So that's pretty darn good, this approximation. And if you notice, the work was a lot easier. On this first one, we had to calculate the original area, and then we had to calculate the area plus 0.1 and do all that. It's not really that hard to do that and then find the difference. But this is easier, especially with much harder problems, much harder, functions. All right. So let's try another one. All right. So here we go. It says z. Let me do black. Z equals e to the negative 2x cosine of 2 pi t. So that's 2 pi t like that. All right, so our differential formula is dz equals z sub x times dx plus z sub y. In this case, it's t times dt. All right, so this is equal to, all right, so z sub x is negative 2 e to the negative 2x times cosine of 2 pi t. This piece here is considered a constant because we're just doing with respect to x. And then times dx plus z sub t would be, so we got e to the negative 2x. Z sub t would be negative 2 pi times sine of 2 pi t, like that. All right. And so now we multiply times dt, and so we can clean this up a bit. So this would be negative 2 e to the negative 2x cosine of 2 pi t dx minus 2 pi e to the negative 2x sine of 2 pi t, all that times dt. Now, was there any, let me see if there were any numbers to plug in here. No, that's just the differential. That's just the differential. All right, so there we have it. Well, let's play around with this a little bit. Suppose that started out with, let's say, p of 1 comma 2, and you ended up at q at 1.1 and 2.1. So we're just moving over a little bit. So I would go ahead and, I'm going to do this two ways. The first way is I'm going to do it just directly without using the directional derivative. Okay, so I'm going to do z of 1.1 comma 2 minus z of 1.1 comma 2.1, and I'll figure that out. Okay, so I'm going to stop the video and do that. Okay, so I got 0.045694. So what this is the change in z, the exact change in z. Just doing it directly. So what's happened here is in the z direction, I've got some surface, and I went from one point to the next, q, this is p, and going up in the z direction, that is this number here. It's this number here. All right, it's 0.04. All right, so now I'll do it using the idea of partial derivatives. All right, so let me move over a little bit. And so what I've done is I've pasted dz over. This is dz. So I'm going to plug in dz with 1 comma 2 in. So this is negative 2 e to the negative 2, this times 1. All right, cosine of 2 pi times 2. Now dx was 0.1, so this is all times 0.1 minus 2 pi e to the negative 2 times 1 sine of 2 pi times 2 dt was 0.1 also. All right, so what I've done is I've plugged in my point P1, 2. I don't have to worry with Q because Q is in here. It's the difference. All right, so I'm going to clean this up and see what I get. Okay, so what I got was negative 0.02767 out of that. And before, I got this 0.045694 number. So the difference between those two, let's check that out. So delta Z minus dz in absolute value. So that the difference between these two is 45694 on my calculator, is a difference of 0.072761. So not a whole lot. All right. So that's the story. So it's kind of like pick your poison, but the differentials are used quite a bit. So the percent error in this is going to be the change in z over z itself, which is approximately equal to the change in z, the dz over z. So what I'll do is I'll do this 0.02. I need to put this in absolute value, 0.027067, and I divide this by plugging in z of 1.1 comma 2, which that was up here, and that was a 0.135 number, I think it was. That's 0.135335 basically, and that's about a 20% error, which, oh, yikes, it's kind of a lot. So normally it's much smaller than that. Alrighty, so that about does it for this kind of material. I'll tell you what I like so that you can probably do a good job studying for it. I like this one because we've done that a lot. I also like the total resistance from electrical engineering, and these are basic good ones too. So I might do an extra video to do extra problems of this. All right, that's it.